So, dear friends, today we will discuss the molecular spectra, and which is very important tool for investigation structure of a molecule. We will start with the energy is radiate in the form of electromagnetic radiation. Any energy, suppose the light is the one of the form of energy from sun, the electromagnetic radiation will come towards earth in the form of a wave that is called as the electromagnetic radiation. Any energy source will give that radiation, transmit the energy in the form of electromagnetic radiation, and electromagnetic radiation is have the wave properties. Molecular spectra is obtained by the spectra is it is a interaction of electromagnetic radiation with matter, and which will give the spectra. Suppose energy, we have said that energy from any source, suppose this is the source, energy is radiated from in any source in the form of electromagnetic radiation, and electromagnetic radiation it is having the wave characters, it is having the properties of waves, where electric field and magnetic field propagated perpendicular to each other, and which is also perpendicular to the direction of the propagation of waves. Suppose that is source from source, a wave is radiated, and if suppose that is the electric field, that is the electric field, and this electric field is the perpendicular to also that is propagation waves, that waves is propagated to this direction, that is electric field and the magnetic field. That is the second one is the magnetic field, which is shown by the M, also perpendicular to the propagation of waves. If suppose the wave, first our electric wave is moves like that, our second waves will be perpendicular to these two waves are perpendicular to each other, and which is also perpendicular to the propagation direction. That kind of wave is the electromagnetic radiation. Any energy, radiate energy in the form of electromagnetic radiation, and that radiation interact with matter. Suppose that electromagnetic radiation will propagate and will interact with that matter. If suppose your matter you have put it in the test tube, some energy, if suppose the number of energy is there, first h mu, the second h mu 2, h mu 3, such energy is given by the h mu, energy is given by the h mu, therefore for each radiation, each bunch of radiation, first is having the wave frequency is mu1, frequency mu2 and mu3, and suppose that matter absorb mu1, mu2, number of frequencies there, mu1, mu2 and so on infinity. Number of frequency is we can obtain from a source. Therefore the number of frequencies, number of that bunch of the energy will number of bunch of energy is there, number of number of waves is there, which is having associated with frequency mu1, frequency mu2, and frequency mu3, and so number of frequencies there. And when this radiation, electromagnetic radiation falls on the matters, if suppose these three frequencies is absorbed by this matter, and if there by absorption this, okay, suppose at the start without the sample your spectra is totally continuous spectra is there, okay, they're all wavelength, you will all frequency wavelength is there, okay, but due to absorption this frequency wavelength, some frequencies, these three will be absent on this continuous spectrum, because this absent frequency is absorbed by this matter, and you will obtain the spectra where which frequency is absorbed by the matter will be seen on this spectra. Okay, therefore this it means there is some vacant places is there, which that means frequency is absorbed by the matter and which will appear on the your spectra, and which give the reading mu1 and frequency mu2 and the frequency mu3, and by the observing the spectra you can predict that the particular matter absorb the frequency mu1, mu2 and mu3 which is not appear in our spectra. Okay, by detector also gives the reading of these frequencies, it gives the chart, that chart is nothing but the spectra. Okay, by the machines, by the detectors, a chart, by using some calculation software is there, you will obtain the spectra, and that spectra will give the particular matter absorb the frequency, that frequency, and this frequency appear in your spectra. That spectra is nothing but the spectrum or the chart or the graph will be obtained from detector, and that the detector gives the information to the computers, and computers give the spectrum, and that is the spectra. Okay, therefore the molecular spectra is nothing but there is an interaction of electromagnetic radiation with matter, and which give the which give the molecular spectra. Okay, remember that very important thing. All the energy is radiated from the source is in the form of electromagnetic radiation, first thing, and electromagnetic radiation is a form of wave which is having all the characteristics of waves, and these waves mutually perpendicular to each other. Okay, your magnetic field and the electric field, okay, magnetic field and the electric field perpendicular to each other, propagator to a direction, and these electric field and magnetic field perpendicular to each other, and also it is perpendicular to the direction of the propagation of waves. Okay, this is our general discussion or basic discussion what is meaning of spectra. Now we will discuss the property associated with the waves, and this will helpful for further discussion. Okay, therefore we will start with the very important thing, that is the wavelength. Okay, we are all familiar with wavelength, is migrate or will propagate like that. Okay, that is electromagnetic wavelength. Second perpendicular wave we not shown for the sake of simplicity. Therefore the first property of wave associated is a wavelength. Wavelength is a distance between two maxima. Okay, that is maxima. Okay, your wavelength start. Okay, the starting point it will move, and at a particular it is maximum, and at a particular point it is a minimum. Okay, therefore the max wavelength is the distance between two consecutive maxima. Consecutive means near, very near. Okay, near to this is not. There is not distance. That distance is not considered as the wavelength. Okay, therefore wavelength is the distance between two successive wave maxima, or the distance between the two successive minima, or the distance between two successive trough, or the distance between two successive crest is also called as the wavelength. Okay, that wavelength associated with the electromagnetic radiation is very small. Okay, actually we measure the electromagnetic radiation in nanometers or Armstrong units. Okay, such units we will use for the find out the wavelength of such very small wavelength associated with the electromagnetic radiation. Okay, therefore for such units, okay, we will discuss here that 1 nanometer is equal to 10 raised to minus 9 meter is equal to 10 raised to minus 7 centimeter is equal to 10 Armstrong unit. Okay, this is the conversion of the units. If suppose 10 centimeter, 10 raised to minus 7 centimeter inverse means the 1 upon 10 raised to 7, that is the centimeter. Okay, therefore this distance is, we divide the 1 centimeter into 10 raised to 7. Okay, 10 and on this that is the 10 minus 7 is there, therefore 1 and 7 0 is there, and therefore that distance is very small, and that distance is measured in the form of nanometer, that is units. General units we will use for the find out the wavelength of electromagnetic radiation, or very small lengths we can calculate it by using these units. Okay, therefore 1 Armstrong unit is equal to, okay, that is 10 Armstrong units, like that, that means the 10 raised to minus 10 meter, 10 raised to minus 10 raised to 10 minus 8 centimeter. Okay, that is 0.1. Okay, that's 0.1 nanometer is nothing but the 1 Armstrong unit. Okay, these are the units, some units which is useful for find out the wavelength associated with the our waves. Okay, this is the first definition we have seen. What is the meaning of wavelength? Second definition, okay, that is denoted by lambda. Wavelength is denoted by lambda, and second is the frequency, that is mu. Very important thing. The frequency is defined as at a particular point. Okay, suppose that point, how many wavelength is passes in unit time. Unit time will base normally 1 second is we consider number of waves pass from a point in unit time, that is in 1 second, is nothing but the frequency. If one complete wave is passed in 1 second, it means the 1 cycle per second. Okay, 1 cycle per second, it means the 1 hertz. 1 cycle per second means the 1 hertz. If suppose 100 waves, okay, 100 full waves, okay, that is full wavelength, 100 is passes from that point within 1 second, that is it means the 100 cycle per second, and that is meaning the 100 hertz. Okay, frequencies unit is the hertz, and 1 hertz means the 1 cycle per second, and so on. 100 hertz means the 100 cycles per second. Okay, therefore this is the units we will use for the frequency. Okay, frequency is nothing but the in 1 second from a particular point, how many wavelength one particular cycle is passes, how many wavelength full wavelength is passes, is nothing but the frequency. Okay, next important thing we have to discuss is the what is meaning of wave number, and wave number is denoted by the mu bar. Wave number is, if suppose 1 centimeter distance is there, within the 1 centimeter how many waves is passed is called as the wave number. If suppose that one wave and the second wave and third wave, okay, third full wavelength, okay, first, second and 3 wavelength, full wavelength, it passes within the distance 1 centimeter, it means that for this wavelength, wave number is equal to 3. Wave number is alternative way, can be also defined as it is the reciprocal of wavelength. Okay, wave number is also given by the reciprocal of wavelength. If suppose for sake of simplicity, if that wavelength, if suppose is a 0.33 centimeter, 0.33 centimeter, and this wavelength is 0.33 centimeter. Okay, 3 wave is present in between the 1 centimeter. Okay, that distance is 1 centimeter, and this wavelength is the same. Therefore, 1 centimeter is the 0.33, 0.33, and 0.30 will be 1 centimeter. Okay, therefore, the one lambda, second lambda, third lambda, that 0.33 lambda is distance by some mathematical calculation we have. Propose very simple one. 1 centimeter is divided into 3 parts, then it is 1 divided by 3 will be 0.33 centimeter, 0.33 and the 0.33 centimeter. Okay, each wavelength is the 0.33. Okay, therefore mu bar, okay, mu bar is equal to, if suppose we have define other way, wave number is it is a reciprocal of wavelength, that is 1 upon lambda, or other way we have defined the how many waves pass within 1 centimeter, or how many waves is there within 1 centimeter, that is nothing but the wave number. Okay, therefore if wave number for this we will calculate, therefore distance is the 1 and the 0.33 is the 1 wavelength. Okay, that is lambda we have taken 0.33. It will ultimately will be the, you found that it will be ultimate the 3. The answer will be 3. Therefore, wave number for this radiation will be 3, and therefore mu bar is nothing but the 1 upon lambda. Okay, next quantity is the C or V. Okay, in the for electromagnetic radiation is radiated at the velocity of light. Okay, therefore the velocity we can replace V by the C, because electromagnetic energy is radiated from a source in electromagnetic radiation, and that radiation has the velocity equal to the light, and velocity is the how much distance is achieved within 1 second is nothing but your velocity. How much distance? Okay, 3 lakh per second, 3 lakh kilometer per second, that is the your velocity of light. Okay, very huge speed for light is associated with very huge speed. Okay, therefore if suppose if you try to find out the relation between the lambda and mu bar, frequency and velocity. Okay, velocity, electromagnetic radiation is mu, and which is equal to the C, because it is having the velocity of light. Electromagnetic radiation is also very high velocity. Okay, velocity is nothing but the distance traveled by the wave within a second. Okay. Therefore, your velocity, okay, if suppose V velocity is equal to is nothing but your frequency into wavelength. One of the formula, that is frequency velocity is equal to your frequency and what you call it as velocity is equal to frequency and the wavelength. Okay, velocity we have said that velocity within a second how much distance is the travel. Okay, suppose that is the 1 second. At that point your 1 second is there. Okay, within 1 second it travel that particular distance. Okay, within 1 second. Okay, that distance is nothing but your velocity. Okay, velocity is equal to we denoted by, instead of V we will use the C, because your electromagnetic radiation also travel with the velocity of light. Okay, within 1 second that distance is travel. Okay, Okay, you can see there is a wavelength is there. Okay, number of wavelengths is there, number of particular one wave second wave, number of wavelength is there. Okay, therefore that is the wavelength, and the frequency is the how much this wavelength is passed within that particular point. Okay, therefore in 1 second, if suppose if you consider if 1 second from this point 4 waves 1, 2, 3, 4 is passes within 1 second from that point, because it will reach there. Therefore also 1 second from there 4 waves full waves or full cycle is passes. Okay, therefore if you find out your velocity, then for first lambda, second lambda, third lambda and fourth lambda. Okay, therefore lambda is there and number of 4 waves is passes, therefore your frequency is the 4, therefore 4 lambda, that C is equal to 4 lambda. Okay, like that way we have developed the equation lambda into frequency. That is we have developed that relation. Okay, therefore that lambda we will transfer to the left hand side. 1 upon lambda is equal to frequency upon C, and we have known that 1 upon lambda is nothing but the mu bar. Mu bar is the wave number. Mu bar is equal to 1 upon lambda is equal to mu upon C. This is a relation between the wavelength mu, that is the wave numbers, frequency and the velocity. Okay, therefore mu bar is equal to 1 upon lambda mu upon C. That relation we have find out here. Next is the very important point is the spectrum of electromagnetic radiation. Okay, electromagnetic radiation we have discussed. Electromagnetic energy is radiated in the form of the electromagnetic radiation. Energy, if suppose there is energy, it means there is particular frequency is there, wide range of frequency is there. If suppose one energy is passed from, if suppose we have heated that particular metal, it radiates the energy. Okay, it's not radiate only single form of energy. It radiates a wide range of frequency. It radiates wide range of energy frequency. Okay, it's not only single. Suppose it radiates only 400 nanometer. It is not possible. It radiates the wide range. Suppose it radiates from the 10 nanometer to the 4 or 500 nanometer. Okay, like that way it radiates the number of frequencies is radiated from a source. Okay, source from we can manage. Okay, from in a hospital X-ray we can find the X-ray of the bones. Okay, therefore there is a source from where the X-ray will be passes and through our body that picture we will capture. Okay, therefore it can be possible to find out to make a man-made source which can radiate number of energy. We can make the man-made source which can radiate only visible region. Okay, like that way we can manage there. There is the spectrum is there of electromagnetic radiation. Wide range spectrum and different region is there. Okay, that region we have calculated or that put forward depending upon the energies. Okay, therefore from that point, okay, therefore at the start there is the wavelength is very small. Okay, then wavelength is increases. Okay, as wavelength is increases, energy is decreases. Remember that as wavelength increases and your energy is decreases. Okay, first region is the gamma region and it's is the less than 1 nanometer. Okay, very higher energetic region is the gamma region and which is having the higher energy. Okay, next region is the X-ray. Okay, in the hospital we have used that particular to find out the X-ray of bones. That picture is found in this region. Okay, therefore 10 nanometer its range is in between 0.1 nanometer to the 10 nanometer. Okay, next region is the UV region and that is the UV region is the UV region is the 400 for this region we have UV region is the for 400 nanometer to the your 700 nanometer. Okay, UV region is in between UV region is a 10 nanometer to the 400 nanometer, and visible region is 400 to the 700 nanometer, and then 10 raised to 3 to the 10 raised to 5, that region is the IR radiation region. Okay, these are the gamma radiation, X-ray radiation, UV radiation. And next is your microwave radiation. Microwave radiation is the less energy than the IR. Its region is the 10 raised to 5 to the 10 raised to 7 nm, and from the 1 centimeter to the so on 100 centimeter, that wavelength is for the radio waves. Okay, radio waves. Okay, therefore in this IR region there is a vibrational spectroscopy is possible. In IR region there is a vibrational spectroscopy. Okay, the region of vibrational spectroscopy is the 10 raised to 3 nanometer to the 10 raised to 5 nanometers. The region of microwave spectroscopy is 10 raised to 5 nanometer to the 10 raised to 7 nanometer. Okay, these lower in microwave, that is the rotational spectroscopy. In microwave region there is a rotational spectroscopy, and in the visible or UV region there is a electronic spectra is obtained. Okay, we will study the vibrational spectroscopy later on and rotational spectroscopy. Okay, this is the wide range of spectra. We have made a compartment according with its energy. Okay, this gamma rays, the higher energetic rays, then X-ray and UV and so on. Radio waves are very small energetic waves than the gamma rays. Okay, then the energy is increases from gamma to the radioactive. This is a spectrum. This is a wide spectrum of radioactive. A wide spectrum of electromagnetic radiation, and we, by using the source, we can manage IR region also. We can only use the IR frequencies or pass IR frequencies to the matter and find out the vibrational spectra. Okay, this region, this spectra is useful for the find out the functional group of a molecule. Then microwave spectra, rotational spectroscopy, we will find out in microwave region of the spectra obtained in microwave region is the rotational spectra, and electronic spectra is obtained in the UV and visible region, and rotational spectra is obtained far higher region to the microwave region. Okay, the boundaries of this radiation, that is IR and micro, the boundary is not precise one. Okay, it can be somehow changeable boundaries there. Okay, therefore that particular very important thing, this is the arbitrary, that is unbound thing, and not precise or imprecise, that region is imprecise. Okay, there somehow region will be that not exactly that precise. Okay, that not exactly they are. There is a boundary between IR and the microwave. Okay, some variation. Okay, therefore we have called this region from this region, from this to this is a far higher region, and far higher region to this 10 raised to 7. We will obtain the rotational spectroscopy. This is the basic, very is required for the study of the spectroscopy. Now, the absorption, we will study the absorption spectroscopy and the emission spectroscopy in next lecture. I hope that particular properties associated with electromagnetic radiation you get that points, and thank you very much.